Welcome to lecture 35. So, this is the last lecture of week 7, and in this week we have been talking about gradient based methods for optimization of unconstant multivariable functions. So, in today's lecture we will briefly talk about Quasi-Newton method and trust region methods, and then we will introduce two MATLAB functions from MATLAB's optimization toolbox for solutions of unconstant optimization problems. So, let us first briefly talk about Quasi-Newton method. The basic iterative process used in the Newton's method is given by x k plus 1 minus x k equal to minus Hessian inverse into gradient of f, both evaluated at current point x k. We know that the Hessian matrix is composed of the second partial derivatives of the function f, and the Hessian matrix in general vary with the current estimate for a general nonlinear objective function. Note that for a quadratic function the Hessian is a constant matrix, but for a general nonlinear objective function the Hessian matrix will vary with the current estimate of the optimal point. The basic idea behind the Quasi-Newton method or variable metric method is to approximate either the matrix H or H inverse, that is Hessian or Hessian inverse, by another matrix using only the first partial derivatives of the objective function. So, instead of using second partial derivatives of objective function f, we want to replace the Hessian matrix or its inverse by another matrix using only first partial derivatives of the objective function f. If the inverse of Hessian matrix is approximated by a matrix B, we can write as x k plus 1 minus x k equal to alpha k into b k into gradient f at x k. The search direction then is minus b k to gradient of f at x k. Now, compare this with the steepest descent method. If B matrix is equal to identity matrix, the search direction is minus gradient of f at x k, which is the search direction for steepest descent method. So, steepest descent method becomes a special case of this equation with matrix B equal to identity matrix. There are two popular methods, Davidson, Fletcher, Powell or DFP method, and Broyden, Fletcher, Goldfarb and Sano or BFGS method. These two methods update an estimate of the Hessian matrix or its inverse. Let us introduce these definitions. With these definitions in mind, the DFP method or the BFGS methods updates the Hessian or Hessian inverse as shown by this expression. It may be noted that both DFP and BFGS methods keep the Hessian matrix positive definite. Now, let us briefly define what we mean by trust region method. We have seen that all gradient based methods use the general scheme x at k plus 1 iteration equal to x at kth iteration plus some step length parameter alpha k into such direction at k. So, in case of gradient based method, we choose a search direction S k that will produce descent, then perform a line search along this direction S k. So, here the emphasis is on finding the descent direction. The trust region methods use a slightly different strategy. In case of trust region methods, we form a trustworthy or safe approximation of the objective function f in a trust region, which is basically the neighborhood of the current estimate, in which the current approximation of f x produces descent. So, once we have the trustworthy or safe approximation of the function f x, we find the minimum of this approximate function. So, here the emphasis is on finding a trustworthy approximation to f x. So, emphasis shifts from finding the descent direction to finding a trustworthy or safe approximation to function f x. So, in case of Newton or quasi-Newton methods, we solve a problem like this. M of x k plus s equal to f at x k plus gradient of f at x k into s plus half s transpose h k s. So, basically compare it with Taylor series expansion and retain only second order terms. In case of trust region method, the model this m x k plus s is basically an approximation of f at x k plus s. So, an alternate problem formulation may be we minimize m at x k plus s, which is given as f of x k plus gradient of f x k plus into s plus half s transpose h s, but subject to s confined in a small region. So, norm of s is less or equal to a parameter delta. So, delta k is the trust region of the model M. That is the region where the model is trusted to be valid. So, basically in case of Newton or quasi-Newton method, the focus is on finding the descent direction. The descent direction S, In case of truss region method, we want to find out the approximation of the function in a trussed region and minimize the function in the trussed region. Now, we will discuss two MATLAB functions from the MATLAB optimization toolbox to solve unconstrained optimization problems. In particular, we will discuss fmin search and fmin unc. In fmin search is a gradient free method, whereas fmin unconstrained, fmin unc uses gradient. Fmin search, being a gradient free method, uses only function value method, function value of the objective function. It is a direct search method. It implements simplex method, whereas fmin unc uses gradient. So, you have to supply the gradient of the objective function, and if we do not supply, it may use numerical computation of the gradient. Fmin unc implements various algorithms such as Quasi-Newton method, truss region method, etc. So, let us first talk about fmin unc, fmin UNC. A basic call is x comma fval is the function name fmin UNC at obj fun objective function comma x 0. Here obj fun is the name of a function file supplied by you in which the objective function is coded in MATLAB language. It is not necessary that you have to give only this name, you are free to supply any other valid name. X 0 is the column vector of starting values, that means initial guess. The first output x presents the optimal solution vector, again it is a column vector, and the second output fval presents the optimal function value, that is the function value at optimally determined point x. By default, fmin UNC seeks a minimum. If you want to maximize a function, you simply code -f in the function file obj fun. So, this presents some more details about the syntax or how you call the MATLAB function fmin unc. Note x equal to the function file name, the built in function file name, the solver fmin unconstrained, fmin unc. It takes two arguments, the name of the function file in which you have written the function that you are going to minimize and the initial guess. Note this, if I supply this, if I write this, I have no way of telling MATLAB that I am supplying the gradient which needs to be used. So, for that you have to add one more argument, options, and through options you can tell MATLAB or this solver fminunc that you are supplying the gradient of the objective function which can be used for minimization. And then this gradient can be written in the same function file where you are coding the objective function that you are minimizing. Now, here are more details about the syntax. If we look at the left hand part, see these are the values that are returned by fminunc. So, x is the optimal function value, fval is the function value at optimum x. So, x is the optimal solution and fval is the function value at the optimal solution. Exit flag is a parameter which tells you about whether the optimization was successful, how it exited. Similarly, output is a structure where you have more informations like number of functions value, number of function calls, number of iterations, so on and so forth. You can ask the solver to return information on gradient and Hessian as well. So, now let us take an example. Let us consider the Rosenbrock function, which is the two dimensional function 100 into x 2 minus x 1 square whole square plus 1 minus x 1 whole square. So, if you look at this function, the minimum value is obviously x 1 equal to 1, x 2 equal to 1 and the function value becomes 0. So, the optimal solution for this Rosenbrock function is x 1 equal to 1, x 2 equal to 1 and at this optimal point the function value is 0. So, take the gradient. So, we have evaluated the gradient. So, in the first step you have to code the objective function. So, open a new M file in the editor and you have to type these lines. First line is the definition of the function file. This is how we write the function file. Function, then f grad f, these are the two values that will be returned by the function objfun and x is the input argument to the objfun function. So, here the Rosenbrock function is coded. Note that it is two dimensional function x 1 and x 2. So, the vector x has two components x of 1 and x of 2, x of 1 equal to x 1, x of 2 equal to x 2. So, we write the Rosenbrock, we code the Rosenbrock function, then the two components del f del x 1 and del f del x 2 are coded as grad f 1 and grad f 2. So, that is all. If you want, you can write end here. So, the first argument f is the value of the function at the input vector x. The second output argument grad f is the gradient vector of f, which is again column vector evaluated at x. Now, you save the file under any name. Here we choose obj.fun.m. All MATLAB functions will have extension .m. Now, in the step 2, we have to tell MATLAB that the solver fmin has to use the gradient information. This is done by specifying one of the optimization options, and the program has to be informed that it has to use this option. So, the general syntax is options equal to optim set grad obj on. That means, we are supplying gradient and the solver has to use the supplied gradient information. This means that this symbol represents the command line. So, you can type it in command line, or you can create another M file, give it some other name and write this statement, and then call the solver fmin to solve the problem, to minimize the function written in obj.fun. So, you are already familiar with the basic sequence, basic syntax, which is x fval equal to the solver name, then arguments are first argument is at, then name of the name of the function where name of the function file where you have written the objective function as well as gradient. Second argument is the vector having initial guess, and third is the options where you have given the option of using gradient information. Now, so there are many other options that you can use. These options are shown here. You can define these options as, so you can define as OPT equal to optim options within bracket at fmin, that means the name of the solver, and then all the options display iter, that means it will show output at each iteration step. Grad obj on, that means it will use analytic gradients. So, analytic gradients will be supplied by you in the function file. Here we have named that as obj.fun. Algorithm quasi-Newton. So, I am asking the solver to use quasi-Newton method to minimize the function, the Rosenbrock's function using quasi-Newton method. Hess update means Hessian update, use BFGS method. We talked about BFGS method, truss region method. Tolfun is the tolerance, main tolerance for gradients. Tol x, x change tolerance, x is the solution vector. Max iter 300 means maximum number of iterations is not more than 300. Max fun evals, maximum number of function evaluations. Derivative check on, so it will check our analytic gradients. So, different options now are available and you can use all these options or some of these options. Now, let us solve the Rosenbrock problem with, let us say, this quasi-Newton algorithm. So, we are supplying all these options and solving the problem using quasi-Newton algorithm. So, I supply x 0 equal to minus 1.5 and minus 4 as initial case. Then use the syntax as shown to solve the problem. So, I have given the name as now say Rosenbrock, the OBJ fund, now I am renaming it as Rosenbrock. You can also give it any other name you want. So, this is the solution you get. So, this is a snapshot of the run of the algorithm, result of the run of the algorithm. So, it first checks the gradient informations because derivative check option was on, and these are the iterations wise results. So, after 16th iteration, optimization is complete. After 16th iteration, the size of the gradient becomes very small. So, now look at the solution that you have got 1 1, and we know that x 1 equal to 1 and x 2 equal to 1 is the solution, and the function value is 0. So, we get that as 2.83 minus 10 to the power 13. So, very close, very small value can be considered as 0. So, these are the some informations which is obtained with the structure named out, iterations equal to 16, function count 20, step size as 1.0617 into 10 to the minus 4, first step length was 1, so on and so forth. Algorithm used is quasi-Newton. So, all these details can be obtained. Let us now solve the same problem using trust region method. So, we just change the option here. Algorithm, it was quasi-Newton method. Now, I change the algorithm to trust region. So, now I am telling the solver that the algorithm that needs to be used is trust region. Everything else remains unchanged. So, this is the result. Now, after 27 iterations, we obtain the minimum, and minimum again is obtained as x 1 equal to 1, x 2 equal to 1. The function value is 1.5226 into 10 to the power minus 19, which is very small. The details are available in the structure called out. 27 iterations were required, function count is 28, trust region algorithm was used. Now, let us look at the use of F-min search. Once you are familiar with use of any solver, you can easily understand the use of other solvers. For example, as of now we have seen how fmin_ung works. Now, we are talking about fmin search. Fmin search does not use gradient information. In fact, it implements simplex method to solve an unconstant optimization problem. But we will see that the basic syntax that we will use are very similar. Again, we define a function file, let us call Rosenbrock, where I code the Rosenbrock function. It does not use gradient information, so no need to supply the gradient information. Initial guess is given as x0 vector, same starting point I use minus 1.5 minus 4. Now, let us say I give these options. So, opt equal to optim set display iter, that means each iterations will be displayed. X tolerance is 10 to the power minus 8, function tolerance 10 to the power minus 8, maximum iterations 500, maximum function evaluations 1000. So, once these are defined in the options, we call fmin search using this syntax. Exat fval, exat returns the solution, optimal solution, fval is the function value at optimal solution, fmin search is the name of the solver at Rosenbrock. So, this is the function file where you have coded the function. X0 is the initial starting point, initial vector is a column vector, and OPT is the options that we are specifying. So, you write these statements as an M file, let us call the M file as rosenbrock.m. Then you either type in these in the command mode, both these 3 lines, or write another M file where you write these 3 lines and then hit the run button, and you will get this solution. Note, it is using simplex method. So, it is talking about expansion of simplex, contraction of simplex, reflection, all these things. We have gone up to 100 iterations, and the solution is again is obtained as x1 equal to 1, x2 equal to 1. The function value is 6.8837 into 10 to the power minus 8, which is extremely small, can be considered as 0. So, we learned how to make use of MATLAB optimization toolbox. In fact, 2 function files, 2 functions from MATLAB optimization toolbox, namely fmin_ung and fmin search. Both are used for solutions of unconstant minimization problem. You can solve for maximization of problem simply by taking negative of f. With this, we stop our lecture number 35